Okay, guys, welcome to another class online, numerical analysis. Let's pray. Father God, we thank you, Lord, for this day. We praise you, Father God, for your goodness, Lord God. We thank you for the students all over the country, Father God, for tuning in, Father God, watching this video, Lord God. And we pray, Father God, that you bless them, Father God. Bless their learning, bless their hearing, Lord God. Guide them, Father God. Reduce any anxiety, any fear, Father God. Help them to work to the best of their ability, Father God, and to find joy wherever they are, wherever this situation or circumstance, Lord. We pray, Father God, that you will give me the words that you have me to speak, Father God. Give us all listening ears, Lord. We praise you in Jesus' name, amen. All right, well, welcome, guys. Today, I'm going to be doing a lot of lectures back to back because we might be on a citywide shut-in, right, stay in your home type situation tomorrow. So I want to make as many videos as I can in front of the lecture board so that you guys can have that to look at if I can't get to, I can't lecture, I can't get back on campus or something like that. So I just want to let you know that I might make a few more mistakes. I didn't have as much time to prep that I usually do. So I'm coming into this a little bit cold on some of the topics I remember doing. But I'm going to try to do my best. If I make any mistakes, if you see any mistakes, let me know. Please email me and I'll make sure to put that on Canvas or somewhere else so that you guys can see that there was a mistake there in that particular part. All right, so let's get started. We're going to continue our topic of numerical differentiation, right? So let's begin with that. Okay. So we're in numerical differentiation. That's 4.1. Numerical differentiation. Okay. And topics for the day, just pretty straightforward. Today is that we're going to be talking about optimum value of H. We'll talk about what that means. Two, and I'm going to do a 3-point difference formula. We've actually already done a 3-point difference formula, but I don't really like to call it a 3-point difference formula. That's just me. So optimum value of H when we do numerical differentiation for a couple of these particular formulas. And then we're going to also look at a 3-point difference formula. So we're going to derive that and then go from there. Okay, so let's get started. Let's remind ourselves of what we've already done. We come up with a forward difference formula, right? Or a backwards difference formula. It depends on how you want to think about it. It's a forward difference formula if H is greater than 0, right? And it's a backward difference formula if H is less than 0. So I have f prime of x is approximately equal to, right, f of x plus h minus f of x divided by h. Okay. This is the forward difference formula. And we actually found out, we derived this forward difference formula by using a Taylor series about f of x plus h. And then we found out that the error, and I gave you guys the exact error, is essentially big O of h, right? Our error is big O of h when we did this problem, when we derived this formula. And then we had something which was the midpoint difference formula. Okay. And that was f prime of x is equal to f of x plus h minus f of x minus h divided by h, right? Where we're evaluating at two different places, x plus h and x minus h. And this should be a 2h right here. Okay. And we found out that the error for this guy, you guys remember, I gave you the exact error, is essentially big O of h squared, right? So when h is less than 1, this error is going to be much smaller than this error right here. So the midpoint difference formula is better. It uses the same number of points, right, x plus h and x minus h as the forward difference formula, but it gives much better results. And that is really nice, right? So the midpoint difference formula is usually the best one to use, if we can use that. If you're, as long as your function exists to the left and the right of your point f of x. If your function doesn't exist to the left or to the right of your function f of x, then you're going to have to use a forward difference formula or something else. So the question then becomes, right, not that we have these difference formulas to approximate the derivative, right? And we did an example where we approximated the derivative of e to the x at 0, right? What is the best value of h to use when we approximate our derivatives, right? So we can pick any h that we like, right? What's the best value of h to choose, right? And the value of h depends on the accuracy of your numbers, right? Of your numbers. How many decimal places are you approximating your numbers, right? Is it 5 significant digits, 10 significant digits? What's the accuracy, right? What's the number of decimal places? We'll just say decimal places that you're approximating your numbers to. We'll just keep it simple. And so it depends on the number of decimal places you're approximating your number to, as well as just kind of the difference formula that you're using. So the optimal value for h for the forward difference formula would be different for the optimal value of h for the midpoint difference formula. So let's put some example for the board here. So what is a good value of h? Okay, when approximating a derivative. Okay. Now let's talk about the forward difference formula first. Okay. Now, if you don't know, if you have no knowledge of the derivative, right? So I don't know what problem x is. Maybe I just know the function values, but I don't know what the derivatives were, the derivatives of that function are, right? If I have no knowledge of the derivatives, then what you do is you would say that h, just pick h to be equal to the square root of delta times x, where x is the number that you're evaluating your function at, right? You're trying to find your derivative, and delta is the accuracy of your numbers. Here, I'm going to just choose delta to be equal to 10 to the negative 15. There's nothing to that, so it's approximately equal to 14 decimal places of accuracy, approximately 14 decimal places of accuracy. So if I have no knowledge of the derivative, choose h to be equal to the square root of delta times x, okay? As long as x does not equal 0. And of course, a lot of times I want to put absolute values around this x too, right? So if I choose an x that is negative, just put absolute values around the x. Right? So choose h to be equal to the square root of delta times x. You can put absolute values around x. So let's just go ahead and do that. Delta times the absolute value of x. Okay. So this is a good ballpark figure to choose for h when we have no knowledge of the derivatives. However, if you do know what the derivatives are, right? If you have knowledge of the derivatives, okay, then you can use this formula instead. H is equal to 2 times square root of delta times the absolute value of f prime of x and f double prime of x. Okay. Here again, we're making an assumption that f prime of x and f double prime of x are not equal to 0. Not equal to 0. Okay. Another thing that we're making the assumption of is that when we do this, that my second derivative actually exists. My second derivative exists. I'm going to choose the same delta in this case. Okay. So f prime of x, f double prime of x, not equal to 0. In this situation, x can be 0. X can be 0 in this situation, but for this particular case. But we do not want either f prime of x or f double prime of x to be equal to 0. At least I don't. Just keep it simple. And then, of course, we have the midpoint difference formula. Okay. And I'm not going to worry about the no knowledge of the derivative one, right? If I'm doing the midpoint difference formula, I just use the same one that I have here. However, suppose I have knowledge of the derivatives. Okay. Then here I use that h is equal to the cube root, okay, the cube root of 3 times delta over f triple prime of x. F triple prime of x. Okay. F triple prime of x. This is what we have. Where f triple prime of x does not equal 0. This is what I want to make sure that I don't have happen. So let's look at each one of these guys. Right? Let's look at an example with each one of these guys. For the 4 difference method, I'm going to use the one where we have no knowledge of the derivative, then knowledge of the derivative, and then the midpoint difference formula, knowledge of the derivative. Okay. And like I said before, this delta is completely arbitrary. It just depends on the accuracy of your numbers that you deal with in your machine. So here's an example. For f of x equal to e to the x, what is the smallest? Or I should say, what is the optimum? So essentially, what's a good value? Value of h. And when I say optimal, I should say what is a good value, because this, for some people, this is not the optimal, but it's close enough for us. Close enough for us. It's very simple, easy to understand. So we'll say, what is a good value of h that can be used? When I have here x equals 3, and when x is equal to 0. And we'll do both the, we'll just do the, say the, what's a good one? The midpoint formula, we'll use x equals 0 to see what would be a good value for that one. Okay. So let's do the first one. For, let's say x equal to 3. X equal to 3. All right. For x equal to 3, let's do the forward difference formula. Suppose, and if I use x equal to 3, I can actually use the one where I have knowledge of the derivative, right? So this is a pretty good one. So I'm going to say, okay, here we go. At x equal to 3, we have h is equal to, we're going to do 2 times the square root of delta. My delta in this case is 10 to the negative 15. Times the derivative of f prime of x. F prime of x, well, the derivative of f of x. So f prime of x is equal to e to the x, and f double prime of x is equal to e to the x. And I'm going to plug in my value of x. So I have e to the 3 divided by e to the 3. The nice thing about this is that they're going to cancel out, right? So it's square root of 2 times square root of 10 to the 15, 10 to the negative 15. And that gives me, what does that give me when I do that? .5 to the times 10 to the negative 8, approximately. What I have. Double check it real quick. Some of you guys are like, yeah, is it? Yes, no. I'm almost there, just double checking my numbers. I actually have 6.3, but close enough. 1, 2, 3, 4, 5, 6, 7, 8, I think. Oh my. 1, 2, 3, 4, 5, 6, 7, 8. Yes. So I actually have like 6.3, but we'll say it's about it's approximately 6.5. Approximately 6.5 times 10 to the negative 8 is a good value of h to use. Okay, and that's going to give me for the forward difference method. What happens when x is equal to 0? Okay. When x is equal to 0. Well, can I use, here I can still use this guy with knowledge of the derivatives, right? I can still use that one. So so this is, both of these guys, I have knowledge of the derivative. Okay. All right, so when I plug in x equal to 0, what do I get when I do that? So I get actually the same exact thing, right? E to the 0 over e to the 0. Both of these guys don't equal 0, my derivatives. So I get exactly the same thing. So if I have knowledge of the derivatives, it's pretty nice, right, for the forward difference method. If I have knowledge of the derivatives, I'm going to be able to use those to be able to approximate my, find a good value of h. Suppose I didn't have knowledge of the derivative, so no knowledge of the derivative. And let's just do it for the first one, for x equals 3. So suppose I had no idea the derivatives of e to the x, right? Maybe I just got function values and I didn't know it was the function e to the x. Only thing I got was function values. So if I have no knowledge of the derivative, what would I use? Well, if I have no knowledge of the derivative for the forward difference formula, I would use h is equal to square root of, in this case, I would have, what would that be? That would be 10 to the negative 15. times, oh my goodness, I apologize, guys. This right here, h equals square root of delta times x, absolute value of x. So it's going to be h is equal to square root of delta times the absolute value of x. I apologize, I can't read my own handwriting sometimes. The x is not underneath the square root. So this becomes h equals the square root of 10 to the negative 15 times, in this case, if x is equal to 3, doing the first one right here, this becomes times 3. And what I end up with when I do that, if I can read my own handwriting, I have 9.5 times 10 to the negative 8. Okay. If I have no knowledge of the derivative. Okay, very cool. Now let's talk about the backwards difference formula. Not backwards difference, the midpoint formula, right? Let's erase this. So for the midpoint formula, I'm just going to assume that I have knowledge of the derivatives. And in this case, we're still doing this problem. Let's do x equal to 0. Just focus on that guy. Okay. For the midpoint difference formula, I need to know the third derivative of f. The third derivative of f in this situation, in this case, is e to the x, right? So we get h is equal to the cube root of 3 times 10 to the negative 15 divided by e to the 0. And when you do this one, you get about 1.4 times 10 to the negative 5. 1.4 times 10 to the negative 5. So just looking at this, right, I don't have to make h to be so small to get a satisfactory approximation of my derivative. So 1.4 times 10 to the negative 5 is the value of h for my midpoint difference formula. Let's look at it. Let's use these values of h at x equal to 0. So at x equal to 0, let's use this value of h for the forward difference formula, and let's use this value of h for the midpoint formula. I'm going to use this guy here and this guy here. So I'm going to say approximate f of x, f prime of x at x equals 0, or f of x equal e to the x using the forward and midpoint difference formulas. I apologize, I don't think my coffee has kicked in just yet. It's going to kick in soon enough. Okay. So I'm going to use this value. So let's look at the forward difference formula, right? Of course, we know that the derivative of e to the x at 0 is 1. So let's just kind of remind ourselves of that, right? The derivative of e to the x at 0 is 1. let's plug in our h equal to, in this case, we're going to use this one because we have knowledge of the derivative. So we have so for the forward difference formula, forward difference, I'm going to use h is equal to 6.5 times 10 to the negative 8, or 6.3, you use that, doesn't matter. Okay, I use 6.5. And so my f prime of x, so x is equal to 0, that's what we're doing, right? X is equal to 0. So my f prime of x is going to be f of x plus h, right? So it's going to be e to the 6.5 times 10 to the negative 8, right? Because it's x plus h. Minus e to the 0, that's x, divided by x plus h, which is going to be at the bottom, which is 6.5 times 10 to the negative 8. And if I did this correctly, this is what I have. I have 1 point, how many zeros is that? 1, 2, 3, 4, 5, 6, 7. 0, 0, 0, 0, 0, 0, 0, 325. That's a pretty good approximation. Okay. And I just stuck that into my calculator. If I use the midpoint formula, midpoint difference formula, okay. Here my h is equal to 1.4 times 10 to the negative 5. Okay. X plus h, x is equal to 0. X plus h is equal to 1.4 times 10 to the negative 5. And x minus h is going to be negative 1.4 times 10 to the negative 5. Okay. So my approximation for this is f prime of x is approximately equal to f of x plus h, which is going to be e to the 1.4 times 10 to the negative 5, minus f of x minus h, which is e to the negative 1.4 times 10 to the negative 5, all that divided by 2 times h. And when I plug this into my calculator, right, my calculator just told me 1, right? I put as many decimal places as I could for my calculator, and it just said that the answer is 1. I mean, I'm pretty sure there is an error, right? We know that there's an error with the midpoint difference formula, but the error is so small that the calculator can't represent it. At least my calculator cannot. So pretty cool. Pretty cool. All right, so now that we talked about a good value of h to use, right? Usually on the test, on the quiz, I would just give you one where you have knowledge of the derivative because I want you to be able to find a derivative and things like that and then plug it in. So on the test, on the quiz, well, no quizzes, right? On the test, if we had quizzes, right? On the test, I'll give you I'll give you the function and then you can find a derivative of the function to be able to find a good value of h to use. Now that we've talked about a good value of h to use, let's talk about a 3-point difference formula, and then we'll talk about the second derivative. So 3-point difference formula. So here I'm going to say that we can approximate the derivative of a function using more than 2 points. If you looked at the last example with the forward difference and the midpoint difference, right? Forward difference is using f of x, f of x, and f of x plus h. The midpoint difference formula is using f of x, f of x minus h, and f of x plus h, right? But who says that we only have to pick just two values, 2 points? We can choose more than 2 points. So, for example, we could use f of x plus h, and f of x plus 2h. F of x plus h, and f of x plus 2h. Now let's see how we can do that. So if I were to draw a graph, right? It's a graph. I got my function. I have x plus h, x plus 2h, right? I have my points here. I can essentially create a secant line connecting the points of x and x plus 2h, right? And I can also create a secant line connecting the points x and x plus h. 2 different lines. And what I can do is I can figure out a way to, and both of these line from x to x plus h and the line from x to x plus 2h represent different approximations of the derivative, right? Right, because they're secant line the slope of the secant line approximates the slope of the tangent line. So I have 2 different approximations of the derivative. And maybe there is a way to combine those 2 approximations together into one approximation. Okay. Combine those 2 approximations together into one approximation. Almost like an averaging effect. It's not going to be an average, it's actually going to be more of a weighted average. Okay. So we want to be able to kind of combine those 2 approximations together into one approximation. And so we know how to find the approximation. We know how to find the approximation of x and x plus h. We know what the approximation of f prime of x is for x and x plus h. So using f of x plus h and f of x, the approximation of f prime of x is, now I'm just going to write out the entire Taylor series. I have f prime of x is equal to, because I want to talk about the error, so don't worry about it, f of x plus h minus f of x, all of that divided by h, right? That is my approximation, right? But again, if I want to say that this is equal, then I have an error, and my error is minus, if you guys remember this, h f double prime over 2 minus h squared over 6 f triple prime plus dot dot dot. Okay, so here is my approximation, just like I said before. Here's my error. Right, we've seen this, we've already derived this last time, if you guys remember. And let's look at f of x plus 2h and f of x, right? Remind ourselves of what that looks like. using f of x plus 2h and f of x. Okay. Using those two guys, our approximation looks like this. F prime of x is equal to f of x plus 2h minus f of x, all divided by 2h. You guys remember that? This is our approximation. And then this had an error as well. Oh, by the way, just to remind you guys before, right? This is how I got that big O of h, right? Looking at that first term, right? This is going to be the one that's going to be our biggest issue. So this is going to be big O of h. It's going to be our error that we get from this. All right, so going back to this one. So we're using f of x plus 2h and f of x. F prime of x is equal to f of x plus 2h minus f of x over 2h. And then I have minus h times f double prime, right? Minus 2h squared f triple prime over essentially 6, right? Because it's going to be 3 factorial minus da 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 da. So here's my approximation for the derivative using f of x plus h and f of x. Here's my approximation of the derivative using f of x plus 2h and f of x. And what I want to do is I really want to combine these two approximations together. I want to combine these two approximations together. I want to combine them into one big approximation. And I can do that when I realize something. I say, okay, I see this approximation. If I were to add these two guys together, right? If I were to add these two guys together, add these two approximations together, I could do that, right? But I'm going to have this f double prime term here, right? When I add them together, right? I'm going to get like a negative 3 halves h f double prime. It would be really nice if I can get rid of this f double prime term. That way I get f triple prime instead, right? Because then I get an h squared error instead of an h error, right? So if I can get rid of this term, I can get an h squared error instead of an h error that I'm getting when I just have these approximations separate. So what I'm going to do is I'm going to actually multiply this approximation by -2 and add it to that approximation over there. So what I'm going to do is I'm going to multiply the first approximation by -2 and add it to the second one. So I'm going to say here, multiply first approximation by -2 and add to the second approximation. So let me do that. Let me just do it here. I'm going to multiply this one by -2. So I'm going to add, so it's going to become -2 f prime of x equals. Okay, when I multiply this by a -2, I get, I'm going to flip this, I get 2 f of x minus 2 f of x plus h divided by h. When I multiply this by -2, I get plus h f double prime. Oh, that makes me happy, right? Because when I add these two together, I'm going to get 0. And when I multiply this by -2, I get plus 2h squared over 6f triple prime. So adding together, adding both equations, what do we get when we do that? Well, this added with this gives me a negative f prime equals. This added with this, I get f of x plus 2h minus f of x divided by 2h plus, now I'm going to add this term comes down here. Notice that I have a 2h at the bottom of my first fraction. It'd be nice to have a 2h at the bottom of this fraction as well. And to get a 2h at the bottom of this fraction, I need to multiply by 4. Okay, I need to multiply by 4. I mean, not 4. I need to multiply by 2, top and bottom. I need to multiply by 2 top and bottom so I can get a 2h there. So let's do that. 2h here, multiply the bottom by 2, multiply the top by 2, I get 4 f of x minus 4 f of x plus h. What happens to these two terms when I add them together? Goes to 0, right? Which is what I want to happen. And what do I get when I do this one? This is really 4h squared f double prime over 6 plus 2h squared. So what do I end up with? I'm going to end up with a minus 2h squared over 6 f triple prime minus that. Let's add these together. So I have negative f prime of x equals, this becomes, when we look at it, if I add these together, right, this is f of x plus 2h. This becomes plus 3 f of x minus 4 f of x plus h. All over 2h. Minus, I guess really right, this is h squared over 3. F of triple prime. And guess what? I have a negative on this f prime, so what am I going to do? Multiply everything by a negative 1. So it looks like this. I get, oh, this should, some of you guys are screaming at me. Where did I? No, I think I'm good. So I get 4 f of x plus 2h, f of x plus h, minus 3 f of x minus f of x plus h. That's f of x plus 2h. All over 2h plus h squared over 3 f triple. Let me just double check to make sure I did that right. You guys are not here to make sure I don't screw up. Unfortunately, right? It looks good. It looks real good. Okay. So here is going to be my approximation. And here is going to be my error. Right, there's more terms here, blah, blah, blah. This actually goes on wherever. I should put another minus sign there. This keeps, can't get it off. This keeps going. This is my error. And my error is going to be less than or equal to the absolute value of h squared over 3 times f triple prime, okay, evaluated at z, where z, okay, maximizes f triple prime, the absolute value of it, over my interval. In this case, it's going to be x to x plus 2h. Notice how many points we're using when we do this formula. We're using 3 points, f of x plus h, f of x, and f of x plus 2h. We're using all 3 of these points, f of x plus h, f of x, and f of x plus 2h. Now I want you guys to go back to our previous lecture, right? And when we did this, we found that the error for the midpoint formula is actually smaller, right? I think it's h squared over 6 f triple prime at z, right? So this formula is not as good. this is not as good a approximation as the midpoint difference formula was. And they say actually the midpoint difference formula is a 3-point formula. You just don't see that f of x term, right? Because it cancels out in the middle. Okay. So here we have an approximation which uses 3 points. The midpoint formula in practice only uses 2 points, although it's called a 3-point formula. But this one in practice uses 3 points. So let me write it down, 3-point formula. So it's actually better to use the midpoint formula if you're going to use one. It has better accuracy. And also, it uses less points. But let's put that. F prime of x is approximately equal to 4 times f of x plus h minus 3 f of x minus f of x plus 2h, all that divided by 2h. And it has an error that is essentially big O of h squared. Well, let me write down what I have over there. My error is less than or equal to h squared over, say, 3 times f triple prime c. And we've already talked about that, which is going to be big O of h squared. So both the midpoint formula and this 3-point formula are both big O of h squared in terms of their accuracy, right? So the 3-point formula and the midpoint formula are better than the forward difference or backward difference formulas here. Let's look at an example real quick of how to use this. Let f of x equal e to x. X equals 0. And h equal to 0.1. Now notice that if you are looking at if you just come from the previous video that we did with the numerical differentiation, right? We used exactly the same function, x value and h, when we looked at the forward difference, and then the forward difference that was x and x plus 2h, and then the midpoint. So I'm comparing the 3-point formula to those formulas from the last lecture. So if you use the midpoint formula, you have f prime of x is approximately equal to, in this case, x plus h is going to be 0 plus 0.1, so I get 4 e to the 0.1, right? X plus h is 0.1. Minus 3 times e to the 0. Minus f of x plus 2h. F of x plus 2h is equal to 0.2. So this is going to become e to the 0.2. All that divided by 2h. Or I should say 2 times 0.1. And when you work this out, you get 0.996405. Not a bad approximation to the derivative of e to x at 1. Not bad at all. Now, you can extend this idea to incorporate even more derivatives, right? The book has one. I'm going to show you another one. We're not going to go through the derivation. Don't worry. Don't be scared. I just want to show you another formula. Erase this stuff here. Put the top back on this guy. Here's another derivative formula. And it uses 1, 2, 3, 4, at least 4 points. We can use even more values of f of x to approximate the derivative. And here it is. Let me show you what f prime of x is equal to f of x minus 2h minus 8 f of x minus h plus 8 f of x plus h minus f of x plus 2h. All of that divided by 12h. And the error for this guy, if you can believe it, so I should say approximately, it's going to be less than or equal to the absolute value of h to the 4th over 30 times the 5th derivative of f evaluated as z, where z maximizes the 5th derivative of f in the interval x minus 2h to x plus 2h. X minus 2h to x plus 2h. Let's compare this one, right? Let's look at this guy. Let's compare it to all the other formulas, right? Notice that this is big O of h to the 4th. So the error for this is much, much smaller than both the midpoint and the 3-point formula that we just created. Now, can you get an idea of what you would need to do to be able to create this guy, right? Find the Taylor series, right, that we did just like before. Find the derivative using f of x minus 2h and f of x minus h and f of x plus h and f of x plus 2h and f of x, right? Add them all together, combine them all together, right? And then you'll get your final answer. Oh, that's a lot of work. I'm not going to do that. No way, no way. But let's look at an example real quick. Again, we have f of x is equal to e to the x. X is equal to 0. H is equal to 0.1. And I think you guys get it about what to do with the x plus h and x minus h. Let me just give you the approximation. So I have f prime of x is approximately equal to f of x minus 2h, which would be e to the negative 0.2, minus 8 times f of x minus h, which would be e to the negative 0.1, plus 8 f of x plus h. F of x plus h is going to be e to the 0.1, minus f of x plus 2h, and f of x plus 2h is going to be e to the 0.2. But all that divided by 12 times h, which is going to be, I think, 1.2. If you plug this into your calculator, you get 0.99999. 1, 2, 3, 4, 5, 6, 6, 6, 2, 6, 9, 6. That's a pretty good approximation just using h equal to 0.1. Remember, we did an approximation using the midpoint and the 4 difference, and it was not near as good as this, right? So this is a really good approximation. Unfortunately, the problem is that you have to evaluate the function at 4 places, right, to be able to approximate the derivative. So in terms of computation, it is more intensive than the midpoint formula was, and the midpoint formula gives you pretty good accuracy just using 2 points. And of course, if you can make your h smaller, then that's even better. So let's talk about the second derivative. We're not going to do too much for the second derivative. I just want to show you how to find how to derive the second derivative. Just the basic second derivative formula, and then we'll go to something else. Okay. So approximating the second derivative. And I know I'm probably not looking at the screen as much as I usually do. I'm trying to go a little bit faster, and so I'm not going, just so I can make sure I can do enough videos to get ahead of the curve, and it won't be too late in the evening by the time I finish. However, please pause the video if you think I'm going too fast. Make sure you have a time to write stuff down. Again, I encourage you guys to take notes if that's what you do. But if you don't take notes, rewind the video if you are confused by something. Maybe when I repeat it again, you're like, I get it. Whatever the case may be, I wish you guys the best of luck. Hope you guys are doing well. So approximating the second derivative. So we want to be able to approximate the second derivative kind of like we approximated the first derivative. And if you guys were noticing, the first time we did the first derivative, there was a way to approximate it using f of x plus h and f of x minus h. And I want to go back to that. So let's look at those Taylor series for f of x plus h and f of x plus 2h. It was when we were trying to find the midpoint formula. And it looks something like this, where we had f of x plus h is equal to f of x, no problem there, plus f prime of x times h, right? Plus f double prime of x times h squared over 2, factorial, right? Plus f triple prime x h cubed over 6, right? 3 factorial. Plus f to the 4th of x, h to the 4th, over 4 factorial, which is 4. And it keeps on going. So I'm just writing, instead of writing a factorial, I'm just writing the number out. F of x minus h looks very similar to this, right? When we work this out, we got f of x, but now it's going to alternate sign. We get minus f prime of x times h, plus f double prime of x times h squared divided by 2. Minus f triple prime of x, h cubed over 6. Okay. Plus the 4th derivative of f at x, h to the 4th over 24, and it keeps on. Now, remember what we just got through doing, right? I want to be able to find the second derivative. I want to use these 2 equations, right, for these 2 Taylor series. And I say, okay, wait a minute. I noticed something. There's a second derivative right here. Here's the second derivative right here as well. Okay. Can I add these 2 derivatives together? I mean, can I add these two equations, these two formulas together? And the answer is I can, right? And when I add these two formulas together, guess what? This third derivative is going to disappear. And the only thing I'm going to be left with is going to be that fourth derivative, which makes me happy because I want to get rid of, if I can get rid of any h terms to the right of my, what I'm trying to approximate, the happier I am. So I'm able to get rid of this h cubed term when I add them together. So I'm going to add these two together. So adding the above equations. We get, okay. This becomes f of x plus h plus f of x minus h equals. I add these two guys together, I get 2 f of x. Add these two guys together, it's 0, perfect. Add these two guys together, I get f double prime x times h squared. Adding these two guys together, I get 0. Adding these two guys together, I get, what's that going to be? 2 over 24. I can write that as 1 over 12, right? H to the 4th plus Now, what am I trying to solve for? I'm trying to find the second derivative, right? I'm trying to find the second derivative of this. I'm trying to find the second derivative. I'm trying to solve for the second derivative. So let's do that here, and then I'll put my final result over there. If I solve for the second derivative, I have f double prime of x times h, right, squared is equal to, and then I have to bring everything else over to the other side, okay? I need to bring everything else over to the other side. So I get 2 f of x minus f of x plus h minus f of x plus h. Oh, minus h. Plus, I have this fourth derivative here. Oh, did I do that correctly? Oh, no, I am wrong, right? Because when I bring this over to the other side, this should be a negative, right? Gotta be careful, right? Gotta follow the rules. Gotta follow the rules. Of course, I could have just thought about, anyway, yes, there's a negative right here because I brought this over to the other side, I brought these guys over to the right side, okay? Okay, now that I have this, I'm going to divide by negative h squared. Let's just do this all in one go. Now notice that these three terms don't have an h multiplied times them, right? So this, I'm going to divide this negative h squared over all of these guys that I have. And because I don't have much space, I have f double prime x. When I divide by negative h squared, I'm just going to write h squared at the bottom. Okay, h squared at the bottom. At the top, because I multiply by negative, right? Then these two terms become positive. So I'm going to actually do f of x plus minus h minus 2 f of x, just rearranging the order, plus f of x plus h. Just rearrange in order. So that's what I get when I divide these three guys by negative h squared. And when I divide this one by negative h squared, I get negative the fourth derivative of f evaluated at x divided by 12 h squared. And then I have other terms out of it. Again, this is going to be my approximation of the second derivative. Here is going to be where my error begins, right? It's going to be all this other stuff. And this error has to be less than or equal to the absolute value of the fourth derivative. Evaluated as z divided by 12 h squared, where z maximizes the fourth derivative, at least the absolute value of the fourth derivative, on the interval x minus h to x plus h. My error is going to be big O of h squared in this case. Big O of h squared. So it looks something like, here's my final second derivative approximation, and we'll do an example. Notice that this looks like a midpoint formula, right? It kind of does, right? Because we're looking at values to the left and to the right of f of x, right, to be able to approximate the derivative. There are multiple, and so this is a 3-point formula. Just like the first derivative, there's different ways of approximating the second derivative. This is probably the easiest way of doing that. So we get f of double prime x is approximately to this. So this is probably the easiest one of the bunch to approximate. My error. And here, when I say error, I'm talking about absolute error. That's what I always mean when I say error, unless I say relative error. But we're looking at the absolute error here. Well, h squared, so this is big O of h squared in terms of the error. Let's look at a quick example. Then we'll be done with this lecture. Now let f of x equal e to the 3x with x equal to 0, h equal to 0.1. Find f double prime x. I should say not find f double prime 0. That's easy. Approximate. Approximate f double prime x 0. Approximate. For those who don't know, right, what is f double prime of x at 0? Well, what f prime of x is 3e to the 3x, right? F double prime of x is equal to 9e to the 3x. So if I plug in 0, I get 9. 9. Not German, and I'm probably saying it incorrectly, but yeah, we get a lot of 9s today, lots of 9s. So I feel kind of German. Let's look in our approximation here. So we have f double prime at 0. So approximately equal to, and so my x is equal to 0. So I get f of x minus h, which is going to be e to the negative 0.1 minus 2 times f of x, so it'll be e to the 0, plus f of x plus h, which would be e to the 0.1. All that divided by h squared, which is 0.1 squared. Oh, I am incorrect, right? Because what's my function? It's e to the 3x, right? So this should be negative 0.1, 0.3. This should be negative 0.3. And this should be e to the 0.3. Okay. That's better. Because when you plug x plus h is going to be 0.1, you plug 0.1 here, you get e to the 0.3, and if you plug negative 0.1, you get e to the negative 0.3. And so now what do you end up with when you do this? I have 9.0677. Not a bad approximation. Not a bad approximation at all. Not a bad approximation. So I'm pretty happy about that. And we are going to stop here. We're going to pick up with Richardson extrapolation, which will be our next talk in this section, in this chapter.